Hello and welcome to this flipped learning episode on investigating and testing materials. So please watch, pause, rewatch, sketch and make notes as you need to. Just to begin, I want to discuss the difference between workshop tests and industrial tests because you could test materials either way. But when selecting for materials for a particular application, it's often necessary to perform tests on a sample piece to assess its mechanical properties. Now, if you did it in a workshop, this is for the purposes of comparing two materials. If you did it scientifically, that would be controlled industrial tests. They give very accurate recorded information. So there's the difference. So workshop tests are just comparing two samples. It's pretty rough and crude. Industrial tests are scientific and they give you data. Whichever one you choose, you've got to control variables as much as you can. And we're going to get into that. So let's say you were testing the tensile strength of a steel bar compared to aluminium. One of the tests we'll discuss in a minute is a tensile strength test. You load the material into a vise, then hang weights and see how it deflects. So some variables you'd have to control there would be the size of the test pieces, the position of the weights, the method by which the weights are added. Are they dropped on or just added carefully? And the time left between each weight. If you can control all those things, you could get pretty comparable results there. Imagine in another case you were testing resistance to moisture, putting one piece of wood with varnish, one with stain, and then you left it in the water. Again, the variables to control here would be things like the size of the test sample, temperature of the water, the depth of the water, like how far it's submerged, and how long it's left there, as well as the amount of finish applied first. You'd have to get all of those things controlled in order to get reasonably accurate results. So just some possible variations is always the size of the material, the environment, the testing equipment, the force applied, methods of force being applied, position of the force, and also the individual taking the measurements. As an individual, we might do tests slightly differently and therefore get different results. So try and control all those things. Let me talk you through some workshop tests. First of all, a tensile test. This is where you'd get a piece of material, put it in a vise, and then suspend weights. Now, if that happens, it should deflect, which means the top of the material is being stretched under tension and the bottom of the material is being compressed under compression. So the more it deflects, the less tensile strength the material would have, and the more rigid it is, the better the tensile strength. Just think the variables to control would be there, like the size of the test piece, the weight applied, and where. In a toughness test, you could just put a sample piece of material and hit it with a hammer, in which case the more force required to break the test piece, the tougher it would be. Again, the variables here would be the size, the force required to hit, and the location of impact. Because if you hit a material at the bottom near the vise, that might have a different impact than at the top. Also, a thicker piece of material, let's say it was a thick piece of aluminium compared to a thin piece of copper, that wouldn't be a fair test. But toughness, it was just hitting with a hammer to see how much force is required to break it. If you wanted a hardness test, one thing you could do is get some sample pieces of material, a hammer and a punch, and just tap it into the surface. And the bigger the dent, the softer the material would be. If it's more resistant to denting, the harder the material would be. So here would be an example: a big dent, soft; a small dent would be a hard material. Again, the variables to control would be the thickness of the test piece, the force required to impact on the punch. You'd want every hit to be the same in terms of the force, and you'd have to use the same punch. Like if you had a sharper punch compared to a blunt one, you might get slightly different results. So that's hardness testing, just with a hammer and a punch. Malleability and ductile testing. Now, just a quick reminder, malleability is the ability to press or squeeze or shape and it to not fracture. Ductility is the ability of stretching without breaking. And what you could do is put a test piece in a vise like that and then just bend it over in that direction. Similar to the tensile testing, the outside would stretch and the inside would compress. And if you see cracks on the outside of the material, that suggests it's less ductile, and cracks on the inside would suggest it's less malleable. If the test piece just broke, it wouldn't be malleable or ductile. Some variables here would be the size of the test piece and the position in which the test piece is bent. For example, if you try to do a really tight bend, that wouldn't be fair with one material if you compared it with another material where you gave it a really gradual bend. So that's malleability and ductile testing. So how might industrial tests differ from workshop tests? Well, in industrial tests, they're in laboratories with specific testing equipment, and all your test pieces would be standard size and your variables would be strictly controlled. And you'd have this machinery with sensors connected to computers to allow for accurate analytical data. So it's not comparing one with another, although you could do it. It's building up real data analysis of materials. Again, you'd have the same rules, like you might have the same temperatures and the same person conducting the tests, maybe doing the test for the same length of time. All of these things might impact your results. Now we're going to look at some of these tests. This is called a tensometer test. This is called an ISOD impact test, and that is a Rockwell test. And so you get an overview of how these work. Now, a good idea would be at various points, you can come back to this if you want, sketch these so you can annotate to explain how they work. So a tensile test, this is done with something called a tensometer. And what you see here on the screen are some testing pieces and a tensometer machine, and then some grips holding the test piece. Here is something called a worm drive. Now what happens is a standard test piece is placed in the tensometer and held with clamps. One clamp is fixed to the other. One clamp is fixed and another moves on a worm drive gear mechanism. So as the mechanism winds, it pulls it apart. The test piece is under tension, and as the test piece is stretched, the load and distance traveled is plotted on a graph. And that gives you information like an elastic limit, yield point, and maximum load. Things like a elastic limit. Metals will stretch and then they'll actually return back to their original shape, but only to a limit. And you see that on the graph here. If I just show you an animation of that, you can see this is the test piece, and imagine a mechanism pulling it apart. It would stretch, it would stretch, it would stretch, and then it goes to necking, and then it would snap eventually. Again, stretching. It's still elastic, it could return, but then at some point it necks, and then that would break. So just some questions to think about on this. Let me go back. Why is it important for the test piece to be a standard size? Again, you've got to control that variable because a thicker piece would be stronger than a thinner piece. What happens before and after the elastic limit? Well, before the elastic limit, the material could stretch and then return. After the elastic limit, it would just snap. It would neck, get thinner, and then it would snap. Necking, that's like where it narrows. So next test is toughness testing. It'd be good to sketch this. This is with a machine commonly called an ISOD impact test. And this is where you test the toughness of the material. A notched test piece, you see that at the bottom, a notch is like a little cut, is held vertically in a vise of the test machine, and then a pendulum is released from a set position and it swings down and strikes the test piece. The energy absorbed by the test piece is calculated from the height the pendulum swings after it's hit. So the material absorbs most of the impact, and then if it absorbed most of the impact and then didn't move very much, the pendulum, that would be tough. If the pendulum just swung straight through it and it snaps and carried on going, that would suggest it's quite a brittle material, not tough. So why must it be held vertically? Why must the sample be held securely in the vise? Well, you want it to absorb energy and nothing else. If it was vibrating, then the energy might be dissipated. So you wouldn't be fair to compare one that was secure and one that was sort of only loosely in the vise. Why is toughness measured by how far the pendulum swings after breaking? Well, imagine the pendulum swinging down. If the material absorbed most of the energy and the pendulum only swung a little bit, it's absorbed it because it's tough. If it just smashed straight through and didn't stop, that's brittle. Here's a little video, and this one doesn't use a needle, it uses a actual computer. So I'm going to skip ahead a little bit in this.
Gauge building to the top of the vise. This helps you just simply place the specimen in the proper position, and you can do that consistently. After you have it in position, We also have a stop in here. Again, that just makes sure that you're placing the specimen in the same position each time. And then you can clamp the specimen in position simply by turning the knob. We do feature adjustment here that if you have testing a brittle material and you have trouble with clamping it and causing cracks, that you can actually consistently apply a consistent torque if you use a torque wrench to tighten the specimen in position. Once that's completed, you go to your display, which has been already set up. You're ready to go. You just follow the instructions on the display. It tells you test mode, release pendulum when ready. So we will release the pendulum, break the specimen, catch the pendulum and relatch. Go to display, select the brake type. In this case it was a complete brake, so we press enter. You look at the display and you measure what the braking energy was.
That would give you your results. So that's the IZOD impact test. For hardness testing, you could do, there's several tests. One of them is Rockwell, one of them is Brinell, and one of them is Vickers Pyramid. I would just remember one or two of them. What you see in the image here is a diamond indenter, and you like hitting material with a hammer and a punch. This presses force into a material and leaves a dent, and basically we're looking to see how deep or how small that dent is. With a Brinell test, they apply force on a hardened steel ball, and that leaves an impression on the surface, and you measure the diameter of the impression left. So if it's hard, it won't leave much of an impression. So there are three common tests for hardness: Rockwell, Brinell, and Vickers Pyramid. In the Rockwell test, a preload is applied to the material using a diamond indenter, and that breaks through the surface of the material. The preload is the zero or datum point. Okay, an additional load is then applied and held for a period of time. The load is released and the indentation measured. So all you need to remember is an indenter is held on the material, leaves an initial small dent, and then force is applied, and they're looking to see how much that dent goes down and springs back. In the Brinell test, a hardened standard size steel ball is forced into the material surface using a preset load, and then the diameter of the indentation is measured. The smaller the indent, the harder the material. Vickers Pyramid is similar to the Rockwell one, the first one. So why must the denter be made of diamond or hardened steel? Well, the indenter must be harder than the material. That's the obvious thing for that. And explain why it's necessary to hold the load for a period of time before releasing. It's got to hold it down so you don't get an instant spring back. The longer it's held down, the more that material has time to deform slightly. Let's watch a quick video on this, and again I'm going to skip ahead to the important parts. There's a lot of science behind this which isn't strictly necessary. You could find this video for yourself, but here's the test.
Let's take a look at how the test is carried out in practice. The tester selects the conical diamond indenter and installs it in the testing machine. Then he picks up the gear wheel and puts it on the support table. After rotating the microscope lens to its vertical position, he can adjust his test piece. As soon as a focused image can be seen on the screen, the surface of the test piece is in the correct height. The test can start. In modern testing machines, the Rockwell hardness test is fully automated. That's why the Rockwell hardness test is used so often in automated production lines. That's it. The Rockwell hardness of our gear wheel is 55 HRC.
So all that's happened there, you can barely see it, is it's left a tiny dent on the surface of the material, and the actual depth. The equipment is so sensitive it can tell what the depth is, and it gives you a measure of hardness. Ductility and malleability. This is the last one. Again, this involves bending material. Remember, as material is bent, it will stretch on the outside, and if it does that, it's ductile, and it will compress on the inside. If it deforms and stays in that changed shape, it's malleable. So a bend test is used to determine how a material can withstand cracking during one continuous bend. A ductile material will have lots of plastic deformation prior to failure. Here, the test piece is placed into a bending machine and held, supported at the ends. A mandrel or plunger loads the test piece at the center and it bends to a predetermined angle or until the test piece fractures. The material is then inspected for cracks and defects. As I said, cracks on the outer bend would indicate a level of ductility. Cracks on the inside indicate the level of malleability. So why is ductility measured on the outside of the bend? That's because ductility is a measure of how much things stretch. And number two, why is malleability measured on the inside? Because malleability is pressing or deforming, and that compression would happen on the inside. Again, one quick video for you. Just very short this, but you can see how the test piece is bent. As you can see there, the material piece was failing, and that shows the limit of its ductility and malleability. So, final test, which doesn't have video, and that's just non-destructive testing. This is for large-scale castings where there's a likelihood of internal defects or imperfections that you can't see. Imagine, I think you've got on the screen there, an oil pipeline, and you wanted to see if there's any cracks in the metalwork. You're not going to cut that up, are you? You'd have to use some sort of test, and you could use ultrasonic sound waves or x-rays, and it will actually scan to show any tiny internal fractures. So ultrasonic testing is when sound waves are pulsed through the material, and the intensity of the reflected sound is displayed on a display. You can see that on his little screen there. Highly accurate and commonly used to check things like welds. You can't take a welded bit of metal apart for defects, can you? You'd have to use some sort of clever non-destructive test. X-ray testing is when an X-ray beam passes through a material and that picks up tiny imperfections, tiny little defects, and that can be magnified on the display. This is for checking microvoids. A void would be like a tiny gap, right? It can be used on composite materials like printed circuit boards and bodies of F1 cars. So the main advantage of non-destructive tests, NDTs, well, you don't have to destroy the material, which would be very expensive to then fix. It's fairly quick and easy to get that sample piece accurately tested. Think about the consequences. What could happen to an oil pipeline if internal defects are not detected? Over time, that crack could grow, it could fail, you could have a major emergency. So non-destructive testing is often used to check the integrity and safety of a material, make sure your product is sound. I would suggest sketching these industrial tests and then annotating, going back in the video and making sure you fully understand it. Best of luck, everyone.